Hi, my name is Vietnam Cao and my student ID is 1012511. Today I will be making a video about our assignment 2 for our machine learning course. This follow assignment is a step-by-step process to implement a multi-class classification using Iris classical dataset. The idea of the current assignment is to intensify what we have learned in deep learning. So the first thing we have to do is we have to locate our iris.csv file in our assignment folder below the current IPYNB file. I already downloaded the iris file in my download folder on my computer. So the next thing we have to do is we upload the file into our collab project, which I'm going to do right now. As you can see right here, machine learning, iris file, upload is here. So the very first time you have to do for this assignment, now the assignment actually starts. The first thing you have to do is we find the path of iris.csv file and save it in a variable called file name. So we import pandas as pd and we call the file name as file name equal to pd.read_csv and iris.csv file. Next is to read the content of the iris.csv file and save it in a variable named iris. I want to see the content first, so I print file name first, and then I create a variable called iris equal to pd.read_csv, and the name inside this column will be, no, I'm sorry, not inside this column, this bracket, will be iris.csv. And our printer will be iris.this. Oh, I should run it first. That's which is my bad. As you can see, it's working. As you can see. The next is to show the first 5 rows of the data frame. The command will be iris.have 5. Be like that. So as you can see, the last column contains strings. Setosa right here. We want to convert these strings to integers, and we can work with them easily in a neural network model. So the task is to convert Setosa to 0, versicolors to 1, and virginica to 2. So you put the command iris.locations, the iris species equal to Setosa species equal to 0, and you can do the same for other color like versicolor or virginica. Not color, this is flowers, so versicolor into 1 and virginica into 2, which will be like this. The 2b now is to check the first 5 elements of the iris dataset once again, like in the previous task, which is here. 3a, select the first 4 columns of the data frame as the data and call the data x. So it will be like this. X equal to iris. Inside this the bracket will be sepal length, sepal width, and the column right here, sepal length, sepal width, petal length, and petal length and petal width. 3b. Select the last column as the label and call it y. So you do the command y equal iris and species, which is the very last column. Now it is time to split the data x and the label y into training and testing segments and call them parts x train, x test, y train, and y test. We split the data label into training and testing segments, and while the size of the test data is 20%, and use random state equal to 1 to 3 to make all the answers similar in the whole class. So you have to import from train test bit from sklearn.model selections, and when you run the command like this, it will be like this: xtrain.have. Please check the first 5 rows of the x train, x test, y train, y test. First 5 rows will be like this. There you go. Like that. 4c. Check the length of the x train and x test. If the numbers are 120 or 30, you're good to go. It's 120 and it's 30. 5a. Convert y train and y test into categorical and call them hot train labels and one hot test labels respectively. You have to, I think for my From my experience, I have to import two categorical from keras.utils.np-utils, which will be like this. 6a. Please define a sequential model that contains 3 dense layers. In the first and second layers, use 100 hidden units neurons and a ReLU activation functions. For the last layer, we need to use 3 as the number of outputs. And the reason is we have 3 classes, Setosa, Versicolor, and Virginica. Also, please pick an appropriate activation function for the last layers. So this is my work. You do from keras.models import sequential models, from keras import layers, and from keras import input. The very first command you do is you define the model and you define the sequential model and you call it, and I will call it model for now. And we'll add model.add layers, that's 100 activation ReLU. You do that one more time, and for the last layers, instead of put 100, you put 3, and activation will be softmax. Now you compile your model using RSP prop, an appropriate loss function, and accuracy for your metrics. So for my loss function, I use categorical cross entropy. It will be like this. And now fit your model using epoch equal to 20, batch equal 10. And now it will be like this. Calculate the 8a. Calculate the result evaluating your X-test one hot test label and see how accurate your model works. I'm not sure about this one. Maybe there's something going on, but this is the accuracy. 9a, now we repeat all we have done in 6a with the following parameters. In the first and second layers, we use 10 hidden units neurons and a ReLU activation function. For the last layer, we just need to use 3. Same as before, we just had to change it from 100 to 10. If we just do the same, like from 9a to 9d, you pretty much do the same as from above, from 6 to 8. It'll be like that. Number 10. Please explain all you have learned from this assignment. These are the questions that you could answer. So the first one is how the number of layers or hidden units could impact the accuracy of our model. Number 1 is increasing the number of hidden layers might improve the accuracy or might not. It really depends on the complexity of the problem that you are trying to solve. 2. Increasing the number of hidden layers much more than the sufficient number of layers will cause accuracy in the test set to decrease. It will cause your network to overfit to the training set, that is, it will learn the training data, but it won't be able to generalize the new unseen data. I got this question. I'll just change it for a bit. Question 2. Do we always suffer from overfitting? Not really. Overfitting happens when a model learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on new data. This means the noise or random fluctuations in the training data is picked up and learned as concepts by the model. The problem is that these concepts do not apply to new data and negatively impact the model's ability to generalize. Overfitting is more likely with non-parametric and non-linear models that have more flexibility when learning a target function. As such, many non-parametric machine learning algorithms also include parameters or techniques to limit and constrain how much detail the model learns. Question 3. How can we find and manage overfitting? Both overfitting and underfitting can lead to poor model performance, but by far the most common problem in applied machine learning is overfitting. Overfitting is such a problem because the evaluation of machine learning algorithms on training data is different from the evaluation we actually care the most about, namely how well the algorithm performs on unseen data. There are 2 important techniques that you can use when evaluating machine learning algorithms to limit overfitting. Use a resampling technique to estimate model accuracy. Holdback validation dataset. The most popular resampling technique is K4 cross-validations. It allows you to train and test your model K times on different subsets of training data and build up an estimate of the performance of a machine learning model on unseen data. A validation dataset is simply a subset of your training data that you hold back from your machine learning algorithms until the very end of your project. After you have selected and tuned your machine learning algorithm on training dataset, you can evaluate the learned models on validation dataset to get a final objective idea of how the models might perform on unseen data. Using cross-validation is a gold standard in applied machine learning for estimating model accuracy on unseen data. If you have the data, using a validation dataset is also an excellent practice. Can be. Please try different setting as we did in number 9. You can change number of layers, hidden units, compile parameters, number of inputs, batch size, everything. Please choose one parameter at a time and share your experience. So I create a different model. It will just be like this, 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 this. Well, surprisingly, for this one, I don't get any warning. Not too sure why. Maybe the professor can help me when he watched this video, but I can tell that a lot of times when you change the number of units you put, or maybe you change the way you compile, or you change the way you try to fit the models, it can affect the accuracy, and I believe also the loss. But that's my experience so far. So that's it for the video. Thank you for listening and have a good day.